So, well, welcome everybody. I'm Sébastien Binet. I'm a software engineer at CNRS in the French body of doing research. And today I will try to talk about what can Go do for science, and that's kind of my excuse to present my own package, GoHEP, which is actually also what HEP stands for is the field of physics which studies the very fundamental laws of physics and nature, and also what are the properties of the fundamental particles which constitute matter, and all of the rules and forces which, which are exchanged between the particle of matter. And of course, there are many labs which are working on HEP. My original field of study, actually, before knowing the truth of being a software developer, being better than a physicist, but okay, let's not delve into that. So there are many labs working on HEP around the world, but perhaps one of the most famous ones is CERN, which is a laboratory near Geneva. And here is an aerial view of CERN, and somewhere in between, at the bottom of the picture, you can actually not really see, but there is a CERN with one of the two labs of CERN, and also the collider known as LHC, which discovered the Higgs particle a couple of years ago. And here you have the CERN collider, which is underground, 100 meters more or less underground, with the 4 experiments which are located at the collider, which is a collider of proton-proton and 27 kilometers of circumference. And I used to work on one of the 4 experiments, Atlas, which kind of looked like that at the beginning when it was still being built. So you have the scale of the apparatus with the little guy at the bottom of the picture. And well, you should know that CERN is open every 5 years or so. You kind of missed it because it was, the last window of opportunity was back in September this year. So you will have to wait for 5 more years to be able to visit it. It's a kind of a great opportunity. I recommend it without being biased, of course. Well, that's for the physical apparatus of the ecosystem in which I used to work and kind of work still, but on the other fence on the other side of the fence. And because it's a software conference, I will talk a bit about software. And to put the scene and the landscape, I will just give you a couple of hints on what used to be software in HEP and a bit of a history about software in HEP. So back in the good old days, we had only one language, Fortran. Who programmed a little bit in Fortran? Still, good. So we are in good company. Sorry for the others. And at the time, you could just write your main program in Fortran in a couple of minutes and compile it in a couple of tenths of seconds, and you would be happy and ready to do some physics with great libraries like CERNlib or HBook or Poe to do physics analysis. And then a couple of years later, in the 90s, people said, well, Fortran, it's too, old days, and let's do some C++ and object-oriented programming, because that's all of what the cool kids in the industry are doing, and because, in some sense it made sense, because people who couldn't go into physics could then, sell their capabilities on the industry writing some C++. So since the 90s, C++ took its roots in the HEP world, and in parallel, starting from the 2000s, Python started to get a grip on the HEP world. So more and more people are starting to do analysis from Python using C++ libraries, or directly doing everything in pure Python. So which isn't, it's not as fast as C++, but it's easier to plug and play a couple of building blocks. And so that's for the very executive summary of what software used to be in the HEP world, but that's only the history, and the current status of the software in a nutshell in one of the LHC experiments is to have a couple of main domain of software libraries. The first one being the generators library, which in which you put all of your knowledge of the physics, so everything from the interactions between all of the particles at the very theoretical point of view, and try to, from those first principles, generate all of the interaction between the particles and the result of the collision between the protons that you have at inside your collider. And then once you've done that, you want to actually simulate the interaction of those fundamental particles with the matter of your detector, and the interaction of the particles which are charged with the magnetic fields, and try to know a bit more about what are those particles. And from that output of this full simulation, which, well, takes quite a time of CPU time, also a bit of memory, depending on how complicated your detector is, because you have to model all of the geometry of those 25 meters by 40 meters long detectors, full of electronics and services and that kind of stuff. All of this is then fed into the reconstruction stage, which model is the work of interpreting zeros and bits and zeros coming out of your detector, your digital detector, into actual particles, I mean real particles, electrons and whatnot. And that's then fed into the analysis, so the main thing that physicists do, so taking real data and trying to, hey, see, there is a boson Higgs, and here, my Nobel Prize. That's the bulk of it. And of course, going more into the ecosystem of the physics world, at least the HEP world, an LHC experiment is not just software, it's also people. And the big experiments like the Atlas or CMS ones are shy of 3,000 physicists. Not all of them are developing code. That's quite the contrary. You have only 1 to 10% of those people actually doing code, which may or may not be a good thing, because not all of them are equally skilled in developing code, but that's for a bit of, for later. And summing over all of those libraries that I just talked about, you have something like 5 to 10 million lines of code in C++, Python, and dwindling amounts of Fortran code. And we used to be proud of ourselves and saying, you see, we have the most amount of code of software in HEP. We are the best. When you compare to the GCC code base, 7 million of lines of code, I guess it was a couple of years ago that I did this calculation, and compared also to the Linux kernel amount of code, you say, well, okay, we have a bit of code, but not that big, and we don't even compare to Google's, for example. So that's for the amount of code, but you have also the real people, the people doing actually the code, and as I said, there is a wide variety of skills among those people. And also a huge turnaround, because usually those people are PhD students, so 3 years on the job, and then once they did their PhD thesis, they go around and do other things. So you have a huge turnaround of people who at some point know very well the code, and then they left the field, and then somebody else has to come by and try to manage that code and be expert on that. So there is a huge turnaround. It's a bit of a mess to try to keep people around, because of course when you're developing the code and there's no real data, people are happy to lend a hand, but once the real data and the physics is pouring in, says, okay, well, code is great, but I need to do physics because that's my the thing that I'm here for, right? So they kind of once they wrote the code, they say, okay, yeah, doing other more important things. So let's say 300 active developers, and around the lifetime of a detector, you have thousands of different developers integrated of that, over that lifetime. Few real software experts with real knowledge about software engineering. A few less, some physicists which have a very strong skill set in developing software. And many more people who are just here because, well, somebody told them, well, you should do some software because you need to sign the paper. To be able to sign the papers of the experiments, you have to do some service task. And why not software, right? So this is kind of the environment of what people in HEP are dealing with. And of course, it's a multi-time zone environment because you have physicists in Europe, in America, in Asia, in Australia. So it's great to debug bugs, because somebody discover a bug in Europe on the around 6 p.m. and then the people in America takes the torch and say, yeah, let me debug that during my time zone. And so it's a huge, interesting, humane effort and very cooperative. But to develop the code in a coherent way, it's not so great for that. Okay, speeding a bit. So about the size of the software, it's kind of huge, at least to deploy it on the what we call the grid, so the distributed clusters that we use to reconstruct event, to simulate event, and to do processing of the events and physics in the end. So 5 gigs of binaries, libraries, and that kind of stuff, plus the extra data to the databases and that kind of stuff to describe the geometry of the detector. So it's sizable. It's not huge, but when you have to push 5 gigs around all the world's clusters, it's kind of an engineering problem at least. So big science, big data, big software, and then of course big numbers, because the application that we use, so I remind you, still C++ and Python, no Go involved right now. It takes quite a bit of time to launch the application, to initialize it, and then loading hundreds of shared libraries, connecting to the databases and instantiating thousands of C++ components. It takes quite a time, plus the memory footprint per process being between 2 and 4 gigs of memory. So that's the constraints that we have. So obligatory XKCD reference is that physicists, well, they do have the choice between either using C++, which is known to be very slow to develop and compile, of course, but fast to execute, or Python being fast, having a fast development cycle because no compilation, let's say, and but slow to execute. So we do learn to love hating our frameworks, which are still developed in C++, every step of the way. So developing it, debugging it, and launching it on the grid, and even more so in the future, because we have to make our software stack, which has been started to be written in the early 2000s, and we have to make it thread safe because of the new kind of new many cores and multi-cores machines. And we have also to train our physicist developers to make it, to know how to develop multi-threaded code in C++. So quite a lot of fun ahead. And of course, all of the other software engineering problems like scalability, installation of the dependencies of all of those C++ libraries that we have to install and use, and a bunch of other things that I won't go too much into details. And of course, obligatory Fitzpatrick slide. Are those our only options between fast and efficient for computers or fast and fun for humans? Well, of course, it's a Go conference, so 14 minutes to go into that. So, of course, Go is, I think, a perfect match for many of those HEP use cases, because it's very easy to learn and very fast to bootstrap people into it. So it's kind of the natural choice, I would say. Unfortunately, migrating those 5 millions of C++ line of codes from C++ to Go during the data taking, because LHC is still taking data, analyzing data, that won't fly. Well, I tried, it won't fly. So we need actually to build a critical mass of HEP enthusiasts about Go to then, for the next experiment or a next detector, try to bootstrap people, and so they start the developing code in Go directly without going through the painful task of translating C++ to Go. So that's where GoHEP is coming in. So I put a few more words about why I think Go is great at that URL. I won't go through the whole laundry list of why Go is great for HEP. It's a simple language that anybody can learn in days, very handy to handle dependencies, fast edit compile cycle. Actually, I'm going through the list, so bear with me. And also all of the tooling about refactoring the code for doing regular software engineering. But more words about it on that URL. So as I said, all of the LHC experiments are taking data, so you can't really migrate those whole monolithic million of code software stacks while taking data. So to convince physicists to prove that Go is useful and pleasant to use and viable, and to prove to them that one can carry an actual analysis which can be published in a regular journal, in Go, you need to provide a couple of building blocks and libraries and reliable libraries, so that then they can take the torch and be pro Go, let's say. So I had to implement a couple of histogramming libraries to be able to do statistical analysis, PDFs, probability density functions, fits, graphs, and that kind of stuff. Also a bit of I/O, and also a bare level of interoperability between Go and the current C++ libraries that we use to store data and that kind of stuff. That's called C++ root. And GoHEP.org is the beginning of such an endeavor. So we have a nice website which doesn't render very well here, but I can assure you it's nice because it's built with Hugo. So of course, nice. And we have already a couple of packages that allow you to do a few things. I won't talk about most of them actually, but I will show some of the output of those libraries. So you can already do a couple of things. We have also a JAWS paper being put out, and also the digital object identifier, the DOI, which are used in our fields. And to demonstrate that Go was applicable for HEP, we identified a couple of poster child applications. So the first one being data acquisition, so the library which takes data out of the detectors and push them to the clients. So that's only I/O, so pushing bits in and pushing bits out. So it's kind of like a web server, except for HEP. And also another application being the detector fast simulation. So the thing which modelize the response of a detector in a very coarse-grained way, but a very fast way. So you can actually launch it on your laptop and try to do a little back-of-the-envelope calculation. So then you can launch a full simulation afterwards, knowing that you're going into the right direction. So that's actually the detector fast simulation toolkit is the thing that I will talk about in more details in the 10 or so minutes that I'm left with. So it's actually a translation of another C++, an already existing C++ application called Delphus. And that's what I'm talking about. So the thing is actually called FADS, for fast detector simulation, because you don't have to make always puns with Go in it, in HEP at least. So it's a translation of this C++ application, and it uses already a couple of libraries that I've wrote for GoHEP. one which is called framework, which resembles the usual, usual for me, application layout of HEP applications. So a thing which manage the processing of the events which come from LHC or other detectors and colliders, which has a first step which is initialization of all of the components of the application. So yeah. And also a phase which tries to process each event as they come out of the detector, and then a finalization phase which write out statistics, write out histograms and that kind of stuff. And for the histogramming, I had also developed a couple of packages, HBook, and also for this application, a package which handles the input and output file formats from the generator. So the thing which handles the fundamental laws of, or described the fundamental laws of the physics. So everything is on GitHub and licensed under the BSD3 license, and also I'm using Godot to display that kind of stuff. So framework is the thing which is which handles all of the processing of the events which come from either your simulation or your detector. And it's, well, concurrent because it's Go, and also inspired from a couple of already existing C++ frameworks that we are using in the HEP world. Basically, well, that doesn't render very well, but okay. Basically, you have a little application which, I mean, a framework, GoHEP framework application is something which launches a couple of tasks which can take data in and push data out. And they, as you can barely see here, you have at the, here you have a task which is named T1, you can trust me on that, which produce a, well, one data object, another data object, and you have another task T2 which takes data from the T1 and produce another massaged way, in some way, data which is called T1 massaged data. So you have something which can be launched like that, have a couple of tasks which are hanging around like that, and can take data in and put data out in a completely concurrent way. So each task can start to handle data from, which can start taking data from event 1, while the task upstream can already start to take or process data from event n+1 and have all of that in a concurrent way. Okay, yeah.
Sorry,
yeah. Okay, so I'm at the middle of the talk. So, so let's say that I described all of the framework stuff with all of the interfaces, which allow you to declare the input ports and output ports in a more or less declarative way, and have all of that being run either in a sequential or concurrent way, and do all of the concurrency stuff still in Go, with a couple of things which look like declarative. And you have at the end of the day, a C++ Delphus-like simulation, which looks like that with the whole data flow. And a couple of results. In red is what I managed to do in C++ in event throughput. The green line is the C++ one, so higher is better, and the blue line is yeah. Yeah.
You should go sometime.
Yeah, because I'm on my watch. I still have 10 minutes, but it's okay. So the green line is the C++ competition. The red line is what I managed to achieve, and the blue line is the naive scaling of when you add more and more concurrent processes. So I'm not scaling very well. Let's say it's okay for that matters, because I'm still better than the C++ one. But I mean, with further improvement, I could probably go further, closer to the blue line. Because right now I'm just launching a couple of, for each task that I just went through here, all of those little square boxes are a task which can take data in and put data out. And I'm launching all of them in, in a free-for-all way. and let the the Go scheduler deal with them and schedule them using the general purpose scheduler that Go has built in. But if I could put more, domain specific knowledge into that scheduler, I could perhaps recoup a bit of scalability from that graph. So let's say that you've been more or less convinced that those two graphs show a good RSS scaling, at least this one. So the green line is again the C++ application, and it's only when I'm hitting kind of the 30 number of processes on my big server that I'm using more memory than the C++ one. So good RSS scaling, kind of good CPU scaling. So, well, right now we are not so much worried by that. And also, which is kind of important in physics at least, a bit by bit matching physics result with regard to the Delphus one. Because in physics, we kind of like good and fast results, but also correct ones, which isn't always the easy thing to do. And we could also do a few more interesting things on the I/O part. I won't go through this example, but I did use my framework to re-implement another application and show that it's using a bit less memory than the original one in C++ and Python, but is twice as fast as the original one. So it's working. That's the bottom line. So Go in science in the 4 minutes that I'm left with. So GoHEP I didn't write it from scratch. I mean, I started it, but I built it on the shoulders of giants from the Khanoom community, actually, which has developed a few interesting packages. Khanoom Blast for the implementation of basic linear algebra. So all of those very core sciencey packages, which can do a very interesting things in science, are already provided to you through the Khanoom packages. So Khanoom Mat to do stuff with matrices, graph to do graphics. I mean, not graphics, graphs. Sorry. Optimization of values, functions, and that kind of stuff, and stat for the statistics, and plot to create publication-ready plots. So the few that you saw were done with Khanoom plot. So they we all agree they are great, right? Perhaps not everybody agrees, but I do agree with myself, and they look great. And a couple of also packages to deal with I/O in science. So NPY I/O to be able to read and write NumPy data files. So to exchange data with your fellow Python analysis developers who didn't see yet the light from Go. Well, you can still interact with them at the file level. And we have also Khanoom HDF5 to deal with the HDF5 files, which are used mostly in geography and in meteorology. And we also developed a Apache Arrow library to deal in pure Go with the Arrow data format, data and IPC protocol, actually. So you can actually use data sciencey packages which are written in Python or C++, provide some data in the Apache Arrow format, and then you can use that directly from Go without having any CGO or C stuff in your stack. And we do also have a Jupyter notebook in Go, so you can actually write data science code in Jupyter using the Go kernel for Jupyter, which is called Gopher Data, Gopher Notes. And we have also a couple of resources for all of the data science community, which is starting to build itself. So in my conclusions, Go is kind of great to write small and large, concurrent or not concurrent programs. And it's also true for sciencey programs. And of course, we can put Go on the map here being fast, efficient for computers, but also fast and fun for humans. And you can actually start to write your sciencey programs, analysis, simulation software in Go using either GoHEP or AstroGo or BioGo or just Khanoom, now in Go. And I will leave you with this quote of Ross Cox, which is true for sciencey programs and also the scientists, because we do work with software engineering also in science, and that's what we do. Thanks.
Do you have any question?
Hello. What about the interoperability with C++ libraries, existing libraries?
So for C++, right now in the Go ecosystem, you do have CGO. So you can write a C++ shim or a C shim which calls C++ and call that from Go. I did write at some point a little machinery which is using Clang and Kling, the C++ interpreter, to reflect into the C++ libraries and try to generate automatically binding code from Go to C to C++. But that's still work in progress. And for Python, we do have also a thing which is called GoPy on the go-python /python/GoPy GitHub repository, which can do the other things. So you write a Go package, and using reflection and Go AST and Go types automatically generates the binding code to present your Go package as a Python module. For CPython 2, CPython 3, and PyPy, and also, well, that's about it.
Sorry, any other question?
Are there applications for which the sort of straight-ahead single processor performance is still not good enough, and thus people are still using C++ or Fortran?
Well, the Go compiler, the official Go compiler, the Go GC compiler, has improved, but it's still not as good on the optimization standpoint than the C++ or G-Fortran one. So for regular single core performance, I think that you're still up. The better choice is still C++ or Fortran, at least for science applications.
Is the shortfall enough to really hinder adoption in places or overall?
On the performance standpoint, I think it's a hard battle to win from the Go standpoint. But if you factor in the development facilities and also all of the software engineering that I tried to show that has poured into Python, into Go, sorry, I think we still have a good option, a good win on that. But for regular straight code, which is being very single-threaded, that we are still on the losing standpoint, I guess. Okay. Yeah.
Sorry, any other question? Oh, it's okay. Which one? Okay. Thank you. Thank you, Sebastian. Sure. You're welcome to